Welcome to our graduate seminar series. My name is Lan, and it's my pleasure to host this seminar. Today we will have an interesting presentation for Mr. Froese from BGC Engineering. His presentation will be on the topic of remote sensing data integration to support regional landslide hazard assessment. Before I call upon Corey, I'd like to give a short introduction of Corey. Corey Froese is a principal geological engineer with BGC Engineering in Edmonton. He has a BSc in geological engineering from UBC and a Master of Science in geological engineering from University of Alberta. And he has spent much of the past 27 years focused on the management of large, slowly moving landslide hazards. For much of the past 20 years, Corey has focused on the integration of both satellite and aerial-based remote sensor technologies to support the understanding of the extent and rates of landslide hazards and the impacts on infrastructure. Corey is also the former director of the Alberta Geological Survey, technical authority for the Canadian Space Agency, and has served as expert panel chair for Norwegian government's rock slopes risk management program since 2010. Corey was the chair of the 11th International Landslide Symposium, and also it is second North American Landslide Symposium, and he has been awarded both the A.G. Sturmack Award and the Canadian Geotechnical Claw Cream by the Canadian Geotechnical Society. Also, I'd like to address some housekeeping rules. Please keep yourself muted through the presentation, and you're encouraged to type your questions in the chat to me or to everyone. We will get your questions covered in the Q&A session after the presentation. Without further ado, I'd like to invite Corey to this virtual stage. And Corey, this floor is yours.
Excellent. I will just figure out all my screen shares again here. And so, Lang, are you seeing my presentation come up?
Not in the presentation mode.
Okay, is it in presentation mode now?
No.
Okay, we had a couple of false starts originally when I did this, so let's try this again. I think this should work now. How about now?
Yeah, it looks perfect.
Excellent. Okay, well, thank you very much for the introduction, and thank you for having me back. Yeah, I just wanted to take this time to share with many of you, some of my experience and some of the work that we're doing operationally at BGC, focused around regional landslide studies and risk management, and how we're really utilizing data and data science and computing power to really support decision making. For those that are students right now, 25 years ago, I was essentially sitting where you are right now, except I was in what I think is the central admin building in the classroom. I'd finished a BSc in geological engineering in 1994, and my supervisor, Wayne Savigny, was a U of A grad, and he recommended that I go back to U of A. So after working for a couple of years in Northern British Columbia, I did pursue an MSc working with Professor Cruden, and parlayed that into the first 11 years of my career working as a geological engineer with PEng. 2005, I made a shift over to the Geological Survey of Alberta to lead and build a new geological hazards program, where I did work on integrating various remote sensing technologies to support landslide hazard management in Alberta, but also led the work at Turtle Mountain, Frank Slide. That organization is part of the regulators, so I spent another few years with that organization, working on kind of regulatory decision making and integrating geoscience data and understanding. Before, end of 2018, moving back into consulting, where full-time since 2020, I've been with BGC, and again, I am based out of Edmonton. Just quick introduction to BGC for those that don't know us. BGC was formed by my undergrad supervisor Wayne and his former and his partner Ian, who were both U of A Geotechnical Center grads in the 80s. Right now, we went from 2 people in 1990 to about 650 people now, and really are quite a unique mix of geoscience professionals and people like data scientists and software developers and climate scientists. And we're predominantly based in North America, but we do have some international presence, but we work around the world. And again, we work in a lot of the areas you'd expect for a typical geo consulting company, but really some of the areas that I'm going to discuss today are really around kind of our focus on software, data management, remote sensing, and data science, and how we're really starting to integrate that into modern practice to support decision making. Definitely not things I learned 25 years ago in your chair, but yeah, if it's take you a bit of my journey from that time to now. So again, one of the unique things that we bring is the ability to organize hazards and earth science data that really makes it accessible for not only society but industry to really support decision making. We have some sector teams at BGC. We are employee owned, and we've set some ambitious goals, not only within the company but within the industries that we practice. And one of the things I'm going to talk about today in more detail is our pipeline sector team, where we've actually made set goals to reduce the occurrence of pipeline failures caused by geohazards by 10% globally. I'm going to show you how we're doing in North America, but it's quite ambitious, and it really is going to rely on us sharing our expertise, but leveraging some of the tools we've developed to support more broad integration of data and data analytics to support decision making. So the thing that I'm going to talk about today really talks about that transition, the spectrum of taking data, converting it into information, and then to knowledge that can actually be used. We often work with clients that get data, and I'm going to talk about different types of data here. And the question is, looks nice, looks neat, how do I use it, right? And when they're actually needing to make decisions that typically need to be quantified, that's pretty important. So we're all pretty GIS savvy now, and we can overlay data, but again, there's a lot more you can do with it, and this is where we're really trying to shift the needle that way. A lot of this is just following, building on formal risk management risk process. Most of you, if you've worked especially in the hazard side, you work in risk, you understand risk lingo, you understand, you identify the hazards, you assess and understand the hazards, and then based on the overall, the types of assets, the overall risk profile, you come up with different ways to manage those hazards. And what I'm going to do for the rest of this presentation is really talk through how through various scales of projects that we're integrating remote sense data to support along this spectrum. So this gives you an idea of the scale of projects we work on. Yes, we work on local projects, mines, work for communities, but a lot of what our software platforms that have been developed around, and our algorithms and our foundational approaches have been based, started with the railways in the early to mid 90s, and then started applying more to transportation and pipeline projects. And currently we are managing the geohazards programs, or supporting geohazard programs for 25 pipeline clients with over 450,000 kilometers of pipeline, with over 152,000 active geohazard sites. So, when you're looking at trying to understand and classify risks associated with that many sites over that many area, you need to really figure out how you harness available technologies and regional data to support local decision making, which is really where we focused our practice. So I'm going to talk today specifically about, how we're doing that. One of the things, we talked about our goals with our clients that we're currently supporting management of the geohazards and related to pipeline failures. The rate of pipeline failures associated with geohazards for our clients has been reduced 5 times the industry average. And really it's following, rigor and a process around, again, as I've mentioned, hazard identification, hazard characterization, and hazard management. And I just I'll walk through how we're integrating not only remote sense data, other types of non-traditional data, and how we're, also, as part of the risk management spectrum, managing hazards from across the different the life cycle and really how we're starting to use more data science and machine learning to start supporting that process. So when I was sitting in your chair and we looked at landslide hazards, we looked at optical imagery, we looked at air photos and stereo, and we looked at topo maps, and we got on the ground and we walked across features. This composite here are portions of a landslide that I was on site on in July. It's a site that we will discuss it publicly probably in about 6 months, but it's a site that many very well-respected colleagues across over the last 40 years had walked and not identified a significant landslide hazard. The highway and the bridge were continuously being repaired, which are those yellow circles. And we did some LiDAR over this site and saw the feature that's in the middle. And after that, combine that with INSAR data to really highlight that not only was there a feature there that hadn't been observed, but it's actually moving quite quickly. And again, just starting to show on the hazard identification how these new tools are being integrated for these sites. One of the things, with operationally using these types of data is just being able to actually, access it readily and be able to not only as engineers do analytics on the data, but also provide clients with the opportunity to do some analytics. What I'm showing you here is a video of one of my colleagues just screen capturing us in our Cambio software, looking at LiDAR change detection data over a pipeline alignment. I think we have probably about 400 kilometers of LiDAR, of repeat LiDAR along this system. And anywhere on the system where we have LiDAR, again, this is the latency, real time in our tool set. We can actually now pull up the data, do analytics on the data, and actually, and again, have it overlain with known data, field observations, site observations, locations of instrumentation to really start pulling together a better story of what's going on. We also have some of this functionality. Again, this is all web-based processing where, again, probably not in the field you're doing with cellular reception, you're doing processing at this speed, but again, you've got the data at your fingertips to be able to start pulling that data together operationally. And this is really pushing us to use more cloud-based computing and working with some people from the software gaming sector to really understand how to manage and visualize big complex data sets. Another type of data that we're really starting to integrate regionally is INSAR data. For those who haven't used INSAR, I'm not going to get into a tutorial, but essentially we have radar satellites orbiting the Earth to which you can, if you look at the same place on the Earth over different time periods, you can actually quantify changes over those time periods. And we can use that, and we often use that to look at ground deformation. This footprint here is a footprint of 140,000 square kilometers of INSAR that BGC acquired Sentinel data ascending and descending that we've integrated into Cambio, again, to support our clients' decision makings and understand on landslide activity level. And I'll tell you why that's important as part of our process in a bit. But, you know, so we've integrated that data, but we've also started working, and if we're going to working across different vendors and different INSAR data types to try to pull together again and be able to display different types of data, different types of INSAR. You know, we're not getting into the details of what all the differences are. We have 3 different bands of INSAR over a site in northeastern British Columbia portrayed on this screen. We have a C band in the upper left, which is a 20-meter resolution pixel C band, which, you know, there's definitely issues with vegetation penetration. There's on the right, upper right, is an X band data that is really tailored to things like active construction sites or structural monitoring. And then on the bottom center, we have what's called L band, which is a longer wavelength band that is very well suited for penetrating vegetation and really quite useful looking at ground movements in vegetated terrain. But, you know, we've built tools and apps where you can actually toggle between the different data sets, you know, back and forth in real time and look at that in relation to slope features, overlaying on LiDAR, etc. Some of, you know, so just, you know, for those that are starting to get out and learning about INSAR, just, you know, this is just a little bit of a, you know, a 101. You're going to hear different people talking about using different types of INSAR and why one's better than the other. L band is wonderful. It penetrates vegetation. It has longer wavelength. It can catch larger range of motion, but you have to pay for the data up front to get it collected. And so it's from the day you pay to get it collected going forward. So it's definitely not a use for every site. Whereas C-band data is being acquired, you know, every 12 days on most footprints around the world, and it has been since late 2015. So if you have to do forensic assessment to understand what the baseline is, how something has been moving, it's often a better tool. You might not get the same data density. This is showing the same site, one set of data looking one way with L-band and one looking the other way with C-band. But the C-band still did give you, you know, some good data to let you know that, yes, this is an active slope that you would have, that we are able to use to understand the rates and changes in deformation over the last 6 years. Another thing we're doing for landslide hazards by integrating the data together is understanding differences in motion. You know, often when we're looking at things like, you know, railways, pipelines, roads, it's the differential movement that we're quite interested in. This is the dry knock earth flow. For those that have access to the proceedings from the Niagara Falls Geotechnical Conference, Megan Van Been and myself and a couple others put a paper in on this earth flow. Essentially, what we did was a client gave us INSAR data, which is the left figure, and said, well, it's not giving me any information on the earth flow, which is what I really wanted. We also then did LiDAR change detection between 2016, 17, and 19. And the reason why we're not getting INSAR data points is because the deformations were up to 5 meters per year on the earth flow, which is well beyond what can be quantified with the C-band, which is looking at maximum measurement about 3 centimeters between satellite passes. So, but with the combined data, we're able to get an understanding of what areas are moving quickly, but also what areas aren't moving, especially the areas around the highway and the railway, which ended up being a quite valuable picture. And again, by having all of these different data sets in one platform and have the ability to actually look at them spatially, but also visualize time series, again, especially looking at big complex landslide hazards and looking at strains and different rates of strain in different parts of the landslide, and also focusing on potential for investigation and mitigation. These become really powerful tools to really understand landslides in a way that we just haven't been able to in the past. when getting into looking at different types of infrastructure, we typically focus on, utilizing our traditional sensors for monitoring displacement. In the past, we would have, we'd take observations, we would put in point sensors like, drill holes with instruments or surface sensing arrays. We'd start looking at, remote sense data. But one of the really valuable pieces of data that we've also been integrated is pipe strain data. For those that haven't worked in the pipeline sector, there's inline inspection tools that are actually run through the pipelines to look at deviations. And essentially, you can start looking at different types of strain that have been developing within the pipe, and start overlaying those with things like LiDAR data or INSAR data to understand, what are the key strain points on infrastructure to support, again, understanding of where and how mitigation should proceed. So that's another, as part of our practice, especially for, more and more pipeline companies now, we're getting expertise in actually interpreting ILI data and spatially representing that in our software tools, overlaying with our other tools to really help understand the extent of hazards. So we've talked a lot about the data and integrating data into platforms, and to this point, it kind of sounds like, well, yeah, you're integrating data into a GIS, which we all know about, but it's really about then starting to build that data into quantitative decision making. A lot of what I've showed you here is our representations in our platform, our software tool called Cambio. BGC, probably of our 650, we probably have a software team of 50 people now. And they're really supporting building out functionality in our tool sets. Our Cambio tool, which Cambio is that advanced without me pushing the arrow, which is Spanish for change, is really our platform that really helps bring together field observations, all these observations I'm talking about, into a common platform where we can actually integrate, again, the various data, the site attributes, and actually come up with a risk or a vulnerability, a hazard and a vulnerability rating based on not only our correlation with our observations and from ground observations and remote sensing with respect to the hazard activity, and therefore come up with a probability of failure. But we also have collected significant amounts of data on pipe failure and pipe failure dynamics to come up with vulnerability calculations, so that every site, and when I talked about the 152,000 sites that we had in hazards, we actually can come up with a combined hazard rating and a vulnerability rating. And those hazards, the probability of failure and the vulnerability are used to come up with the probability of failure ranking, which then all of these sites are relatively ranked with respect to one another across the system. And again, operators might have linear assets over thousands of kilometers. So what the tools allow them to do is come up with a ranked understanding and spatial distribution of their different probability of failures, and then based on their own internal risk tolerance, come up with actions and timing of actions based on that. So we run inspection programs for pipeline operators across North America, inspections and undertake mitigations. And those are really the timing of those and where the clients and operators invest is built directly on the timing that comes out of our Cambio algorithm. So we've talked a lot about monitoring and understanding deformation. There's definitely other types of satellite-based data that we're relying more and more on to understand landslide hazards and really understand the timing of activity change with respect to landslides. Because typically, especially in this part of the world, infrastructure is built to withstand kind of ongoing loading with respect to landslide hazards, but it's often the sudden movements that are really what cause issues. So more and more we're trying to understand what drives sudden changes and starting to utilize satellite-based hydroclimatic data to really help with that understanding. For those that haven't spent much time looking at regional early warning, there's I think I said on the next slide, there's a really nice reference, kind of a summary paper put together by Fausto Gazzetti and a group in August 2020 that looks at territorial early warning systems and examples internationally. But foundationally, there's three kind of pillars of landslide early warning. There's the landslide model, which is understanding the linkage between the water, the moisture infiltration into the slope, and what that does with respect to the activity or velocities on the slope. On the left is just a little model showing the different types of moisture that accumulate and infiltrate into the subsurface. And on the right, just showing some extensometer readings showing changes, accelerations, and various changes in velocity over different time periods that are correlatable to different hydroclimatic events. The next part of understanding, what should be worried about it. Once you understand, what are the linkages between things like precipitation, soil moisture, snow melt, and what drives change. The big thing then is operation to understand what matters. What range of deformation can a structure tolerate? A highway, a bridge, a house, a pipeline. And that's not standard across all infrastructure, even pipelines, different diameters, different age, different materials. So this gets into really understanding, again, what are the tolerance for deformation, setting thresholds, and then starting to look at what are the combinations of hydroclimatic parameters. And this is really getting into machine learning. And I'm going to show you some work we've been doing in Western Canada. And this is what our data scientists are doing right now, is taking displacement data from across the Western Canadian Sedimentary Basin and correlating with different hydroclimatic attributes to try to look at relations to come up with predictors of landslide activity. Once you come up with warning models, it's starting to pull in regional data, forecast data, to try to forecast and understand where those sets of parameters that you've determined in the warning model might coalesce and come together and exceed a threshold. And this is another thing that we're doing in our tools, is really integrating gauge data, remote sense data into our tools, not only to visualize, but also to send alerts as to trends. So that's when you're looking at warning system and what's involved with actually sending a warning. It's that understanding of the landslide model. It's the understanding of what matters, the warning model, but then that feeds into the warning system. So I'll just give you a couple of examples of where we've been applying these techniques and how we've been using this various data. The Western Canadian Sedimentary Basin, large, deep, basin filled with, a lot of Cretaceous age sediments, especially marine shales that are quite weak. Also often thick glacial deposits, which are weak. And pretty much anywhere where there's a river valley in Alberta, you're cutting through these weak materials and you're getting widespread landsliding. We have, of course, a large number of operators that work in this region. Our staff have worked extensively in this region. So we've started working with a group of clients to pull together displacement data. So each of these green data points is a site where we have multiple displacement sensors. We collected data from 340 slope inclinometers, 44 shape accelerator installations. I believe it was 15 GPS monitoring sites. Plus, on the right, I showed you the regional INSAR data before. We also have data points from regional INSAR data covering many well-known landslides. So we're also starting to input time series points from INSAR. The other thing that we're doing is there are satellite-derived hydroclimatic models and data going back over 20 years, covering the entire Earth. So because what we want to do is be able to look back at what we know about displacement and displacement history and try to understand, again, what were the factors that contributed to activity change in the past in order to project forward. What are those? So again, these are data sets that we've linked directly with our tools, and our staff are able to pull directly into the tools to start assessing. So what we're able to do once we pull all that data together is start to look at what are the factors that have led to velocity changes. The upper portion of this graph are SAA monitoring points at different depths within a borehole. And this is an installation that was installed in 2014. On the bottom, purple is snowmelt, gray is 60-day precipitation, blue is 24-hour, green is soil moisture modeled at a depth of about 2 meters, and the yellow is a modeled parameter which represents essentially wetness or dryness of normal, which is a combination of precipitation, soil moisture, evaporation, and snowmelt that essentially looks at change versus norm. So the higher values are wetter year than normal. In general, the lower yellow values are drier than normal. So we've started looking at what are the various correlations between things like specifically soil moisture and precip that have really driven changes in landslide activity. And what we've done is gone back for over 40 slopes in the basin and started to look at, what combination of factors are common where we've seen accelerations, and then starting to test that commonality, those common points versus known deformations to say, would we have been able to predict this if we had used this threshold? And one of the big things that we find, like soil moisture matters. It's a big deal. On the bottom graph, we actually, we have a 60-day cumulative precipitation threshold we often use that's around 200 millimeters of precipitation accumulation over a 60-day period, wherein a time period similar to what we have now or what we've had last year, with a kind of middle range soil moisture, we would have triggered, we would have had prior warning for accelerations. But in relatively dry years, you've had the same precipitation and no accelerations. And it's just really, and these are things that we're looking at eyeball now, but these are in the machine learning part of the next phase. It'll be actually starting to pull together the data for these various points to really understand the correlations. Right now for our clients, we're trying to develop this understanding so that they have some data-driven operational thresholds, but the intent is to really move this into machine learning and build predictive sort of spatial exceedances. And this is the type of thing that clients use this data for. We have in 2020, for example, there were many large rapid accelerations of landslides across the region that led to damage and even rupture on events. And therefore, operators are being driven internally by management, but also by regulators to have something in place. And we've been working with them to provide various operators to provide different levels of threshold exceedance that would, that if you have a critical site that is in need of mitigation, that you have kind of almost a better safe than sorry threshold versus thresholds that are consistent with some of the big landslide years like 2020, 2013, 1999, that you'd likely trigger a broader system-wide approach for. So anyways, this just tells you how we're starting to integrate some of the historical Earth observation data with geotechnical data to provide operational response to clients. So we've just talked about the Western Canadian Sedimentary Basin, where we have, pretty consistent conditions geologically, significant amount of data, and we understand what's going on. It's been studied pretty well. Not saying that the US hasn't studied well, but these are examples of one of the systems that we're also developing thresholds for in the US right now. Crosses many different physiographic domains and also has different geological controls, topographic controls, and different landslide types and processes. And the historical data, the temporal data, like I just talked about this data set we collected with actual velocity data. The current data set is USGS and NASA reported landslide occurrence, pulled from news reports and other sources. And our challenge right now is how do we come up with something that's data-driven and representative across these various georegions without the type of displacement data we have now? We're trying to look at things like landslide occurrence based on the published record. What years and what months were there more reported landslides, and what were the hydroclimatic parameters associated with those? That's not really clear right now how that's going to work. One of the things that is also not clear is to the quality and applicability of the different types of Earth observation derived models. We're finding that a lot of these events, it really is the intensity of rainfall for some of these shallower slides, not as much soil moisture driven, and some models really underpredict intensity, whereas some models are much better for looking at intensity. So not only are we challenged with the landslide occurrence data, but we're also having to really understand what the Earth observation satellite derived models are and what they're not, and how to figure out how to calibrate them to ground conditions. And that's what we've been doing to this point. Again, trying to look at occurrence of landslides, looking at different thresholds, looking at exceedance, and trying to at least come up with some preliminary thresholds that we can start looking at across the system. But really, without having the really good data to come up with definitive thresholds, we really rely on pulling together and integrating various types of data, again, into a common platform to support decision making. Over the last 6 months, I've been leading a team that's been responding to storms in the US. Kind of every major tropical storm and hurricane that's been hitting landfall and intersecting regions where our clients operate. We integrate storm track data from NOAA in the US. So on the right, or so the left is actual precipitation accumulation. The right is forecast, and that's overlain on where we have critical sites and knowledge of landslides. And what we end up doing is integrating that data with our known critical sites, and where we have continuously monitored sites with things like slope accelerators or strain gauges, and really tracking the accumulations and slope performance, and essentially near real time assessing what is too much, what's okay, and operationally recommending response for our clients. But again, it's having all that data in one place that's allowing us to do that. Often the response time is pretty short, and you can't be running around and looking for all this data. You need it in one place, and so that's how we're able to make really timely operational decisions right now. And it also is allowing us to, by taking the accumulations that we've obtained from the satellite data, to look at actual accumulations, to look at accumulations versus thresholds, and really to support targeted operational response for clients. So again, this just shows a map of where are recommending to clients that they do get on the ground and do have a look, because one thing you don't want operationally with any asset owner is to send them out too often. If you continuously send them out and ask them to spend money looking at things that aren't real, they will stop listening to you. So again, by having the data all together, monitoring data, hydroclimatic data, understanding of the slopes together in one platform, we're able to actually, make informed decisions and provide reliable and timely information to clients. So with that, I guess this is the end of the presentation. I guess, what do I want you to get out of this? We're getting more and more data. We're going to continue to get more data. And, it's, if you actually understand how to harness it and how to organize it and to integrate it, it can be exceptionally powerful. Without that, it can be exceptionally overwhelming. Software, the things we're able to do even over the last year, like the on-the-fly LiDAR change detection I showed you, the process that's been built by my colleague Matt Latto and his team, it's just amazing what we're able to do now versus 12 months ago by really harnessing cloud-based analytical tools, learning from groups like software or entertainment software designers as to how they integrate data, working with our data science folks on really how to organize and make data accessible and usable across platforms. And really, how more and more we're not only just integrating, our traditional geotechnical data, our investigation data, our observation data, remote sense data, but how we're starting to integrate more and more different types of data that provide us clues as to what's going on and what has happened, but also to start utilizing that to build predictive analytics to look at future change. I mentioned that at BGC, we have a climate scientist as well. And what we're trying to do is build these models to look back 20 years as to what precipitation, snow melt, soil moisture, et cetera, has driven landslide behavior, but also then look at future models for where we're expected to see greater amounts or in terms of frequency or spatial extent of these same processes or less to help asset owners plan. Often when you work with transportation authorities, they don't necessarily want you to, they're not necessarily equipped for you to tell them that next week there's going to be 20 landslides in this region. They're going to deal with that when they get the call. But what they do want to know is if they're continuing to spend money mitigating a site that is only going to be expected to grow larger and become more active in the future, how should they maybe be planning their investments in mitigation, in rerouting or managing the hazard now? So again, that's more and more if we continue to integrate data, to embrace data science and also climatic models, that's where I see these tools going in the future. So with that, I will figure out how to stop sharing here and go back to our chair and happy to answer any questions.
Excellent. Thank you, Corey, for such a great presentation. I really enjoy it. And it's nice to hear about all this type of software or platforms or algorithms to integrate the data and facilitates the analysis and helps the judgment and decision making. So I do have a question here from audience. And so the first one is, based on the huge amount of data required for driving this tool, I suppose that the quality data is very important. How do you assure that the data quality is enough for getting to support the good models and forecasts?
Yeah, no, great question. I think one of the things I mentioned, just for background in my introduction, is I spent a number of years at the Alberta Geological Survey with a group of where data and quality and understanding data quality was paramount. And the thing is, as long as you understand and you can declare how the data has been collected and what the quality is. It's still data, right? But it's really important to understand that. On our team, we have a data science group. We have data analysts, which their job is really to bring in data, to assess quality, and to have it ready in a format that it can be utilized. And with that, you have the associated metadata as to the source data and how it's been derived, and again, are able to assign essentially a quality parameter to it. And then our data scientists then take that data to run the analytics. But again, you do need to understand how that data has been derived. And that's an interesting as well. Like we look at the data we derive as geoengineers, and we really try to understand the quality of that data and make sure we're using process standards to collect data. But often when we ingest other types of data, we often take it for granted that it's fine, and that is something that you can't do. When I talked about pulling in satellite-based hydroclimatic data on intensity duration of precipitation, we've been really looking at testing that against known sites where we had precipitation-driven events and what data would or would not have predicted that event, and some data sets won't, just because of how the model's been derived. So I'm not sure if I've answered all the questions, but it's, if you are getting into big data, having teams of data analysts that can help with the data, having access to subject matter expertise in the field in which the data has been acquired. That's why, again, looking at our hydroclimatic data, we have our climate scientists that we work with to really understand the source of the data, how it's been derived and how it's been presented, because that's critical. To really understand where it can be used and where it shouldn't be used.
Thank you for your answers. That's a great one. And there's another question, or two questions actually are concerning the same. They're just trying to ask what's the definition of the INSAR and the LiDAR. Like, can you clarify the difference between the quality between this two types of data, LiDAR and the INSAR?
For INSAR, so INSAR, I think you asked about
what are the INSAR and LiDAR?
Okay, so INSAR is short for interferometric synthetic aperture radar. So essentially, you're using non-visible light, microwave radiation, to send signals and bounce signals back off the Earth. What I showed you was satellite INSAR. Sometimes you'll see ground-based INSAR. I know that U of A has a couple of ground-based INSAR units that are essentially the same. Instead of a satellite orbiting, sending out microwaves to the Earth and bouncing back, they have a rail that images slopes and sends back information. And with that, that's non-visible light, and the wavelengths, again, the ones that we use range from about 3 centimeters for X band to 6 centimeters to C band to 25 centimeters for L band. LiDAR is light detection and ranging. It's visible light, right? So whereas radar doesn't need a light source, day or night, fog, you can get a signal. LiDAR is light. You have to have visibility between the sensor and what you're imaging. And it's a different wavelength, it's a different resolution. And again, many different uses, right? Whereas we use, traditionally in the past, have used LiDAR more to get high resolution digital elevation models to characterize morphology. And now we're doing it to look at change, but we're able to look at change kind of over about 20, 30 centimeters between passes. INSAR is that it's not going to give you a really high resolution digital elevation model, but you're going to start being able to look at millimeter level trends in deformation based on the wavelengths that you're imaging. But I'm not sure if there's a lot of detail, but essentially LiDAR is visible light, INSAR is non-visible light, and they're complementary technologies, but they're definitely use them differently.
Great. I think you answered this question and makes sense to us. And we have another question concerning about the multiparts Linda data. This is very specific. So the question is, does BGC have some multiparts Linda data on post-wildfire geohazard sites? Is that type of data available for research? And
so yes, we have access to that type of data. Whether it's available for research, it would just depend on who the client is, right? Because a lot of clients are quite open for research. So what I would suggest, I did have my email address on the last slide, but if not, you can get it from the organizers. If you have a specific request, I will link you up with one of my colleagues. I have 2 or 3 colleagues, Carrie-Ann Lau and Joseph Gardner, as an example. They really focus their practice on post-wildfire debris flow occurrence and are doing, of course, a significant amount of work in British Columbia this year on that. And with that, we do have repeat pass LiDAR and other types of data to support. So yeah, I'm happy to pass on those requests. And if there is interest, link you with Joe and Carrie-Ann and see where that would go.
All right, thank you, Corey. So please feel free to contact Corey. You do have your email, right? So can just type into the chat box.
Okay.
He will probably follow you up later. The question, I think probably the last one I have here. You mentioned INSAR, L-band, and LiDAR are great for vegetation, but does it actually penetrate through the vegetation, or does it capture ground data reflection when the pulse finds a way through the canopy? I think you probably already answered this when you're trying to find the difference between LiDAR and INSAR.
The reason why, so with LiDAR, of course, just the density of returns, you have so many points coming down that you are getting points that are going between the trees and hitting the ground and getting returns. With the INSAR, you think about the wavelength. If you see my finger going back and forth, if for shorter wavelengths, there's more, waviness. So as you're coming down to the ground, you're hitting things like branches and you're getting scatter of your signal. Whereas on longer wavelength, it's more, it's not as irregular horizontally. It's less variation horizontally. So you definitely have a higher likelihood of getting ground returns and minimize scatter from hitting branches. That's the Coles Notes version, but yeah, L-band is that, and L-band for INSAR is ideally what we would have widespread. Is just quite expensive now. That being said, the NASA and the Indian Space Agency have partnered on a satellite called NISAR. That can be a combined L-band, S-band satellite that the plan is to launch in January 2023. And with that, there will be global coverage of free L-band data. BGC, we're an early adopter as part of the NISAR program, so we'll probably be mid-2023 getting our first taste of the data and testing to see how to work. But I'd expect by 2024, we talk about Sentinel data being freely available. You're going to have L-band data freely available globally. That is really, I think, going to be a real paradigm shift in operational INSAR integration, especially in this part of the world.
Great. All right, I think that's all the questions I have here from the audience. And if anyone still wants to ask questions, you can just feel free to unmute yourself. We still have some time. If not, I would like just to conclude this seminar. Thank you again, Corey, for joining us and giving us such a fantastic presentation. And I really appreciate your time. And also thank you for everyone who come to join this seminar today. And yeah, it's a good topic that we're probably not really studied in the courses. All right, and so I would like to just conclude this seminar, and hope everyone have a good day. I'll see you next time.
Thanks for the invite. We appreciate it. Take care, everybody.
Thank you, Corey. Thank you, Len. See you guys next week. Bye-bye.